So our next speaker is Mary Becker, and also not too far from here at San Diego State. And Mary's going to be kind of keeping us in the 2D regime of nanophotonics.
All right, wonderful. Thank you, everyone, for coming today. Good morning. To reiterate, my name is Mary Becker. I'm an undergraduate student at San Diego State University. I'm currently working in the Behura lab, which focuses on the photophysics of quantum materials. Today, I'm going to be talking a little bit about characterizing and engineering quantum materials for photonic devices. To begin, why you should pay attention to this. In our world today, we're using and outputting hundreds of thousands of tons of CO2 to currently run our current computational models, and we do not have the energy means to support this increase in computation needs. Now, in classical models of computation, we utilize bits, which store informations in zeros and ones. Now, back in the 80s, Feynman theorized the idea of a qubit, which utilizes the probability space anywhere between 0 and 1 and called that a qubit. Now, we're finally able to realize a qubit using the material characteristics of certain devices. And our lab is hoping to take advantage of these materials for producing photonic qubits. Now, two of my previous speakers have talked about this material a bit, so I'll dive in a little bit deeper as to how we're going to utilize it. Hexagonal boron nitride is a material that's analogous to graphene in its structure. It's often referred to as white graphene. And what's special about this material is that it can host defects, often called color centers. And within those defects, you have a phenomenon known as single photon emission that occurs out of localized states. We want to utilize this single photon emission within these color centers, within photonic qubits. And then within this, integrate those photonic qubits into further quantum technologies. Now, first, you actually need to readily produce hexagonal boron nitride in a scalable and replicable way. Now, most labs, as I've seen in other presentations here, utilize exfoliation, where you take a bulk crystal of hexagonal boron nitride, you apply Scotch tape, you peel it off carefully, and then you peel, and you peel, and you peel to get down to a monolayer. Now, although you can get a very pure sample, it's not necessarily replicable, it's not scalable. You can't necessarily get the same flake twice, which is what you need if you want to increase your ability to have a growing, scalable technology. It's also incredibly time-consuming to actually find a monolayer. So our lab is utilizing chemical vapor deposition. Now, this process takes a precursor in a phase 1 chamber. Our lab uses ammonium borane complex. It sublimates it into a vapor phase, opens it up into a secondary phase chamber, anneals it to a high temperature, and most other labs that utilize this process deposit those on a catalytic substrate, as shown here with a copper foil. This allows for easier replication. It can be pretty high quality, although not perfect like the bulk crystal exfoliation that we've seen before, and we can hopefully directly integrate this into a quantum circuit at a larger scale. So the goal of this project specifically was to produce hexagonal boron nitride with these tunable color centers, or the defects I mentioned before, in a scalable process. And in order to do that, we broke it down into determining, we have to actually be able to see if the hexagonal boron nitride was deposited. We have to determine if the defects were even there on the surface. We have to correlate the growth of this material onto our substrates to our specific manufacturing parameters so that we can accurately replicate this process. And we need to make sure that these samples themselves can be directly integrated into quantum circuits in the future. So it's a lot to ask, but let's begin. Now, the typical method of chemical vapor deposition using catalytic substrates has a problem. If you directly try to characterize this using Raman spectroscopy, copper fluoresces quite a bit. If you put it directly under there, you can't necessarily see if you have hexagonal boron nitride on the surface. You often have to transfer it onto a dielectric substrate that's not going to interact with the Raman so that you can determine the presence of a hexagonal boron nitride peak within the Raman spectra. Now, what a majority of labs do is that they directly deposit onto a catalytic substrate, like a copper foil. They spin coat a polymer known as PMMA onto the surface of that. They dissolve, they etch away that copper foil, usually using a strong acid, and then they put another substrate underneath, melt away that polymer, and then you can finally get something you can characterize and work with. Now, the problem with that is you can't necessarily control all the new defects you have induced in this process. So we're hoping for a better method, one that's a little bit more direct. So to really get into how our lab is effectively characterizing these substrates, this is a methodology a lot of other people use. It's Raman spectroscopy. It's a non-destructive method of determining what exactly is on the surface. You are able to shine a monochromatic light onto the surface of the substrate, and then by visualizing the scattering of that light, you can see the vibrational modes of that actual material, and you can get a kind of molecular fingerprint of what's going on the surface. So we're specifically utilizing that to determine what we are growing. So a little bit about growing hexagonal boron nitride directly onto dielectric substrates. It's a little bit harder. As you can see here, you use significantly higher temperatures, longer growth times, and more precursor than you would with any catalytic substrate. And it requires a lot more tuning to actually get it on there and in a very even deposition. And then beyond that, you'll also notice that we have to vary pressure quite a bit, and as well as the gases that we use. But luckily, we've actually been successful, even with all these changes. One note to all of you when seeing that high temperature, if you're buying a CVD system and you tell them that you're producing hexagonal boron nitride, make sure to tell them you're doing something unique so that you don't end up melting some O-rings, because sometimes those systems are not designed to go to this high. So if you're doing something novel, make sure you're safe. But we were successful. We were actually able to deposit our hexagonal boron nitride directly onto silicon oxide. And with that one-step process, we were able to take that substrate, readily characterize it with Raman, and then after confirming that hexagonal boron nitride was on the surface, as you can see here, peaks around 1,366 relative inverse centimeters denote hexagonal boron nitride. And these variations around 1,366 often denote the number of layers. So not only were we able to get hexagonal boron nitride on the surface, we were actually able to manipulate the thickness of growth that was occurring, that we're hoping to tune more and more as we continue on in this process. And another thing that's great about having this dielectric substrate is that we can then take this readily deposited hexagonal boron nitride. We can then create heterostructures if we so care to, as my other previous speakers mentioned, or we can just directly integrate it into circuits. Now, how exactly does this work? We know how catalytic interactions occur, so we need to propose mechanisms as to how we can directly deposit hexagonal boron nitride. So we utilize interactions between the boundary layer. As you can see here, the boundary layer is directly influenced by these changes in our growth parameters, such as temperature, growth time, pressure, and the like. So we are able to take the vapor phase of the ammonia boron complex as it becomes products like borazine and other polymers of the like. And then once it gets into that vapor phase, we allow for that boundary layer to be readily deposited on by increasing that temperature, increasing that growth time. We create the conditions necessary for those, for borazine to actually absorb on the surface and react with each other. And from there, it can nucleate out. Now, I want to point out a little difference between, as you'll see in this graph here, there's a slight difference in these curves. Now, our lab has been playing both with silicon oxide as a substrate and also silicon nitride. And you'll see a slight difference here in the H-band thickness over time. Now, we propose that the interaction with oxygen and the silicon oxide actually allows for faster growth deposition because of the very interaction in those adsorption and nucleation. We're going to be playing around with other dielectric substrates as well to further confirm this proposed mechanism for how it can actually grow directly on the surface. So what we found is that by optimizing the chamber pressure, temperature, growth time, and the amount of precursor, we can find in scale uniform hexagonal boron nitride on these dielectric substrates. The Raman spectra indicates the presence of defects in H-band by not only taking that Raman spectra, but then converting it into electron volts in the same graph to be able to see the different kinds of defects. And then we're also hoping to expand to other kinds of dielectrics beyond silicon oxide and hopefully into silicon nitride. And we want to develop tunable defect formation by varying these growth parameters and introducing defect elements. I'd like to thank the MARC program, the CalBridge program, the NIH for funding, as well as the Air Force Research Laboratory and San Diego State University's undergraduate research program, especially the Bahura Lab and my mentors that are here, and the very large delegation from San Diego State University. Thank you so much for coming and supporting me. I'll take any questions you have.
Questions from there? Hi.
Immediate question is, do you have your GPA on your silicon substrates?
Mhm.
You know, in general, quantum, for instance, when they grow graphene on goals to screw up, so how do you propose getting it off of the silicon substrate?
Well, that's the fun of it. We don't have to. We can just keep it on the silicon substrate, which is great. I think that's the point of this research, that because it is on that silicon substrate, that can all just be integrated, or it can all just be characterized. We have no intention of removing it.
Go ahead.
I'm not sure if I missed it, but what wavelength of light laser were you using?
Oh, 532 nanometers, so that's green within the optical spectra. Yeah, and around 4 milliwatts of power as well.
Can you say more about the thickness of that image? Is that a variation of 0 and 1 monotype?
Yes, so what you're seeing here is you have, in the area C region, we were able to see a mono layer, and then it got thicker when you went to B, about 2 layers, and then definitely bulker on A and D, as you can see in this progression of the Raman peak. Yeah.
All right, let's thank our speaker.